We will continue with the final lecture by Shadab.
Thanks, Ajith. Welcome back, everyone. So I was thinking, what can I talk about today? And I thought, I've told you in the first lecture that large-scale structure can do a lot of things, and I only showed you a few things. We have talked about some of these things in more detail, but I thought it would be a good idea to give a flavor of some of the more advanced things we are looking at these days, which are sort of closer to the data, but also trying to understand galaxies a bit better so that we can do better cosmology. But also some of this is fundamental physics related to that. And so this is a list of topics I thought I can talk about quickly, but it's a large list, so I might not finish everything. I'll try not to rush. So if I don't finish everything, that's fine, but I'll see how much of that I'm going to talk about, but also talk about each of these things a bit briefly, not going into a lot of details, but feel free to ask questions if you want to understand some of the more details. So let's start with neutrino mass. So all of you probably have already heard that cosmology can measure some of neutrino mass very well. And so what are the sort of different ways to measure neutrino mass using large-scale structure survey is something I'll just show, and I'll also show what is the current limit. So to give you a brief background, is that what is the problem we are trying to tackle here, right? So we know that there are three flavors of neutrino. There are three eigenstates, and there are three mass eigenstates. These mass eigenstates and flavor eigenstates are not same, and so they are mixed with each other, because of which when neutrinos travel, they oscillate between different flavor eigenstates with respect to different mass or energy eigenstates. So there are measurements of difference of mass eigenstates, very precise difference of mass eigenstates from solar experiment, and there are also measurements of this difference of 3 to L, which is the mean of the first two from atmospheric experiment. And so what we know that there are three eigenstates, and we know the difference between them, but we don't know the absolute scale. So we don't know what is the lowest mass, and hence we don't know any of the mass absolutely, and we also don't know what is the sum of the total mass. So we want to sort of understand what is the value of these masses. But another interesting thing is that since you only know the difference, this is one way to arrange this difference. You could also arrange this difference in this way, where there is a lower mass which is has a larger gap to the upper two mass, and so these are called normal hierarchy and inverted hierarchy for neutrino. And given these differences mass measurement, if you assume that the lowest mass is pretty much 0, then you will come up with that the sum of neutrino mass has to be at least 0.06 electron volt, because that's the lowest mass you could have. And if you work out the same thing in inverted hierarchy, then this is the lower bound of 0.1 electron volt. So sum of neutrino mass will either be at least 0.06 electron volt or 0.1 electron volt, depending on what the condition is. And so you could also think about, if you want to figure out which one of these is true for our universe, if you can rule out that sum of neutrino mass is 0.1 electron volt, so you can put an upper limit also, not even measure, which is lower than 0.1 electron volt and significant upper limit, then you'll know that it's normal hierarchy and not inverted hierarchy. That's another angle to think about, and that's something we were trying to do in cosmology using large-scale structure. Okay, and another thing we know is that given we have measured CMV very precisely along with BBN, we know photon density in the universe very well. And so once you know the number density of photon, number density of neutrino is essentially fixed up to a factor of N effective. And N effective is another thing probably you have heard about a little bit in the inflation lecture, and you'll hear more about it in the CMB lecture. How do we measure this, which is the number of relativistic species. So this L is essentially a statement that you only know the sum of, like, mean of these two. So you don't know, there's not a difference from individual one. So that's why I don't have either 3, 1 or 3, 2. Yeah, so you only know this total difference, effective difference, rather than any one of those states. So yeah, so this is what I was trying to say. To begin with, neutrinos comes in 3 flavor, right? Electron, muon, and tau neutrino. That's what color is representing. But there are also 3 mass eigenstates, and the mass eigenstates are combinations of the flavor eigenstates. What we measure when we measure the flavor through any of the interaction, and we want to figure out what are the mass eigenstates, which is why they oscillate. Okay, so yes, please. I think for these kind of thing, we don't care about. I don't think so, but maybe I don't know enough details about that kind of particle physics level about neutrino. But I will show you what is cosmology is sensitive to, and what is cosmology is sensitive to is roughly the sum of the total mass. And so the details about whether it's Majorana or Dirac, maybe if you can probe neutrino in very early universe where what is going to happen, the decoupling or neutrino becoming non-relativistic will be function of these masses, and so different neutrino may become non-relativistic at different scales. But that is something right now we don't have access to. Sorry. Yeah, so it can only measure one pair of mass. Yes. Why do we have upper bound rather than lower bounds? So that will be clear when I talk about how we constrain masses in mass. What is the effect of mass in neutrino? But let's say you want to measure any quantity generally. Well, probably it will not be true very generally, but when you take the limit of that quantity to be 0, the effect basically goes to 0 from some vanilla model. Let's say there is no neutrino in cosmology. And so as you increase the mass, the effect becomes prominent. So if you want to measure very small mass for the neutrino, you have to have very precise measurements. So as the precision increases, you can, I guess that does not really explain why we have upper bound and lower. I think that will be clear once I talk about how cosmology constrains neutrino, if you are okay to wait for a few minutes. Okay, so how does, so there are sort of 2 ways cosmology can constrain neutrino, and these are called geometry and growth. So I'll talk about each one of them. So in terms of geometry, you have already seen this picture, right? So we have power spectrum, we have initial matter power spectrum, which goes as k to the ns, and as it goes through the whole process of Big Bang nucleosynthesis and CMB, after photon and baryon gets decoupled and neutrino and proton free stream, then you get to a stage where essentially there's a turnover in the matter power spectrum, and this scale is representative of matter and radiation equality. Which means if I were to have more matter in the universe, this scale is going to get pushed further in terms of the lower scale. If I have more radiation in the universe, then it's going to get, scale gets pushed towards the left. And so what is happening here? What we are really essentially thinking about, if you have more radiation, then what's going to happen is that the whole process of decoupling is going to take longer. There's a more energy density in radiation, so it will take longer for it to decouple, and hence the scales at which the time by which it decouples is going to be larger, and so you're going to have this decoupling at larger scale. So you're going to push it to larger scale, which means a smaller k. Whereas if you have more matter and less radiation, this whole decoupling is going to happen sooner, and hence you're going to start seeing that at smaller scale. So this scale is going to basically get affected. And if you add neutrino to the radiation, then neutrino, since these are relativistic at this epoch, is going to go to the radiation side and is going to change the balance of this scale. And so this is the scale where, in principle, we can measure from large scale structure, right? So this is just essentially balancing the density of matter components, so both baryon and cold dark matter, and balancing the neutrino plus photon. So you have already seen this equation, which is essentially the sound horizon. If I integrate in terms of how far these waves, these acoustic waves, is going to travel with the sign speed in that medium, and what is the h of z Hubble expansion as a function of redshift up to the equilibrium, then that is what is giving me sound horizon. So this is the RD on which we are essentially calibrating BaO2. So you can see where I'm going with this. Your Hubble expansion rate itself is a function of total matter density in the form of neutrino. And hence what's going to happen is that your RD is going to get adjusted depending on how much mass is there, what is the total mass in the neutrino, because the number density is already fixed, right? And so using BaO measurement, which we have looked at, including Fisher forecast and in quite a bit of detail, if you have very precise BaO measurement, then you are able to constrain sum of neutrino mass. Another way to constrain neutrino mass is what is called growth of a structure. And so what's going to happen is that if you introduce something like neutrino in the universe, then to begin with, they are relativistic particles. So they have like really large thermal energy. And as the universe expands, things cool down, depending on the masses of the neutrino, they will start becoming non-relativistic. So there's a scale at which neutrinos are going to become non-relativistic. And so because of this relativistic nature to begin with, and slowly becoming non-relativistic, it essentially adds an additional energy term. And so if you think about dark matter, which is growing under gravity, it's growing and collapsing and forming structures like dark matter halo. That structure formation, if you convert some of the dark matter, a fraction of dark matter into neutrino, is going to slow down. So the more the mass you give to neutrino, the harder it will be to form a structure, because neutrino is going to oppose the collapse of any structure. So it is going to oppose any growth of a structure as well. But this is going to happen only at certain scales. So in terms of power spectrum, how it looks like is that if you have essentially a non-relative, and so these are the scales which is probed by CMB versus galaxy survey versus weak lensing versus Lyman alpha. And so if you have neutrinos, then depending on the total mass of the neutrino, it will suppress the structure. So it will reduce the amplitude of the power spectrum. And this will be function of what is the mass of neutrino. Right? So the larger the mass and higher the suppression. And this transition is function of where neutrino becomes non-relativistic. No, so this is nothing about neutrino as dark matter. There is a CDM and then there is neutrino. And it is only saying that what is the total mass of sum of mass of the neutrino, and hence what is the fraction of neutrino in the universe. So if you think about total energy density, it's divided into matter, baryons, dark energy, and in this case, there is also going to be neutrino. But in this picture, dark matter is still CDM. So dark matter is not, we are not trying to explain dark matter as neutrino. Right. So this will bring you back to one of the equations I showed when I was talking about BaO. You're essentially looking at the growth of structure, and in the simplified picture, where I'm basically ignoring baryons, then the overdensity of the matter is going to grow, but it is going to suppress by a fraction, which is neutrino. So in absence of neutrino, F mu equals to 0. This is going to be just 4 pi g rho naught delta m. Otherwise, there will be a F nu. And so what's happened, the modes, the power spectrum modes, which is growing in absence of neutrino, which is growing with the scale factor A, now it will grow with the scale factor A times A to the power 1 minus 3/5 of the fraction of the neutrino. And this is what is causing this suppression. And so if you write down formally overdensity in terms of the power spectrum, what you're going to see is that there's this effective suppression. So by measuring this suppression, amount of suppression, you can measure F nu, which will actually give you sum of neutrino mass. And this suppression is expected to happen at scales where neutrino becomes non-relativistic. So now this quantity is something what we measure, right? So effectively, the growth of a structure is what redshift space distortion is measuring. f, which is logarithmic derivative of d with respect to the scale factor. And so this f, which I told you yesterday in GR, is just omega matter to the power 0.55. In presence of neutrino, it is going to get modified, and because omega matter, it's only the, it's, here I consider omega matter to be the total matter density, so it's baryon, basically anything apart from radiation or dark energy. Now, there's a fraction of matter density which is in the form of neutrino, which is not helping the growth of structure at all, and so it's going to get suppressed. So RSD, which is going to allow you to measure growth rate, is going to be sensitive to neutrino mass and hence suppression of growth. So those are the two ways. And now why do we have upper limit? The reason we have upper limit, if you think about it, in this kind of figure, the neutrino mass 0 will basically bring you to, in terms of the relative amplitude, will bring you to this line. And there's always going to be the error bar on these lines, right? So the smaller the error bar is, the smaller is going to be the upper limit. But you cannot put a lower limit unless your error, unless you see the signal and your error bar is smaller than the difference from this line. Does that make sense? So if you have a, let's say, power spectrum like this, P of k, this will come with some error bar. Okay, this will always have some error bar. And now you are saying that in presence of neutrino, depending on how much is neutrino mass, it's going to get suppressed. So it's going to look something like that. This amount of suppression, if you want to put a lower limit, what you have to do is that you have to have this error. First of all, whatever value you're looking at suppression, at that value, this error needs to be smaller than this difference. So if this is the difference, this is the delta P with respect to neutrino, and this is your error, sigma P, then your sigma P has to be smaller than delta P, where the delta P is the amount of suppression given the true neutrino mass in the universe. Okay, and so since our error is always large to begin with, you will not get any lower limit for that. But you can get upper limit by saying, okay, if I have some error here, sigma P, and my deviation, if this error is large, right? If your error is large, then you know that the neutrino mass cannot be larger than it deviates, it suppresses more than that. So that's why it's easier to get upper limit. That's why neutrino mass has upper limit. And in fact, that has some other implications which I'll tell later in terms of Bayesian inference. You can essentially say that your deviation in terms of the power spectrum is smaller than certain upper limit, and hence the mass is smaller than upper limit. Does that help or no? Some of the masses of neutrino is smaller than some number. Okay. This one? Ah, right, this one. Yeah, this limit. Yeah, so this limit is now, so this limit is coming from a different angle. This is not coming from this kind of measurement. What we are saying is that you know these differences, right? So you know how to arrange this relatively. So you know this difference of this quantity with respect to the midpoint of this, and you know this difference. Now take the lowest mass to 0. Assume that lowest mass is 0, because that's the minimum mass you could ever have. And then you sum it, then these are the lower limit. And if it's inverted hierarchy, then that's the thing. Sorry, Ajith, you're saying something? This is effective lower mass of the sum of neutrino masses given these measurements. And so that's useful to keep in mind, because then you have a target to achieve in cosmology whenever you're thinking about error. So these lower limits, so maybe you're asking about this lower limit rather than the upper limit. Yeah, so this lower limit is coming from basically effectively whatever the minimum mass you could have given these hierarchy. No, so you cannot set M1 to 0. All I'm saying is, okay, what will be the minimum mass, given we already know the difference. What is the minimum possible in presence of I'm violating the fact that the neutrino mass cannot go to 0. But basically, if this is 10 to the minus 6, don't even go to 0. Let's say this mass is 10 to the minus 6, effectively it doesn't add to the any sum. You'll still find the minimum neutrino mass will be this. Yeah, we are just taking that limit. Okay, yeah, so this is just a bit more visual illustration of what I already told you. If you were to say, let's say, look at the universe and simulate it. So this is a simulation from this particular paper, where we are looking at, what you're looking at is the density distribution of dark matter field. So there's it's an n-body simulation where wherever there's a red, there's a lot of stuff. So these are like big halos, and then there are filaments, and then wherever there's a black, there is less things. So things have started with initial Gaussian random field with initial power spectrum, and then they have grown over the time, and you'll see a structure like this, and you can calculate equivalent power spectrum. So, but if I throw neutrino to this simulation, and this is a example where neutrino have pretty large mass, something like 150 MeV, then you'll see a structure like that. So what is the difference between these two? So this has less stronger structures. So things have not collapsed as much as in this case. You can see there are empty regions here. You can already see, and these are very red, versus there is not so much empty region. So if you take this simulation and go in the past, let's say if you go to a past snapshot, you'll find something similar to this. So basically the growth is suppressed. The structure formation have slowed down. By putting so much neutrino, you have said, okay, you cannot grow so fast, you have to grow slowly. And so that's the effect we are seeing. And of course, this is your eye is guided to some small scale effect. If you look at very large scale, if you coarse grain things, then you'll see no difference, which is why at some large scale, the power spectrum will be same. It's only going to get affected once you are in a scale which is non-relativistic for neutrino. Okay, so that brings me to, so I hope that gives you some intuitive idea of there are two ways to constrain neutrino, because neutrino is going to affect where is the location of sound horizon, and hence BAO is sensitive to that. And neutrino is also going to affect how fast the structure is growing, hence things like redshift space distortion is going to be sensitive to that, or direct measure of power spectrum itself is going to be sensitive to that. But the growth part is something we don't use so much to constrain neutrino, because there are other complications. So there's non-linearity, there's galaxy formation, all of that is also going to affect power spectrum at this large K mode. But the geometry part is pretty clean, because BAO is fairly clean. It's at a large scale, fortunately it's at 110 megaparsec over H. And so we can directly apply without worrying about much of these non-linearity or galaxy formation. So we are very fortunate in this sense, right? So imagine if universe happened to be such that the decoupling happened much earlier. The sound horizon was at a scale which is non-linear now. We would have been in a very difficult position. We would have to pretty much, BAO would have been at a scale which is sensitive to all this non-linearity, and we would not have such a clean signal. But that's not the case. BAO is at 110 megaparsec over H, and hence we can use that, and it's a very clean probe. So if you think in the context of BAO, this just the geometry, I'm just trying to illustrate the same thing what I said. If I assume the mass of the lightest neutrino, which is on the x-axis, it can be anything. I don't know what it is, but let's say I can take any value I want, and I impose the measurements of difference of masses from these atmospheric and solar experiment. And if you look at different hierarchies, so you look at normal hierarchy versus inverted hierarchy, sum of neutrino mass will follow these two curves. So in inverted hierarchy, it will saturate 2.01. In normal hierarchy, it will saturate 2.06 electron volt. So if you sort of look at this, and in the context of what our current measurements of sum of neutrino mass is, so these are 2 sigma upper limit from a combination of BAO plus redshift space distortion. So this includes growth and CMB and supernova, so all of that. So we are using luminosity distance, we are using angular diameter distance, we are using CMB-RD, so sound horizon measured from RD. We're combining all of that and saying, okay, what is the mass of neutrino? And this is marginalized over all other degree of freedom you could allow in cosmology. Okay, so this is not for fixed thing. And so for this situation, you find that this sum has upper limit of 0.12 electron volt. So we are getting close, but we are not yet there to say a statement about whether it's inverted hierarchy or normal hierarchy. No, so this is just the upper limit. This is just the upper limit. And this is just a prediction that what will be minimum sum of neutrino mass. So there's no, so this is, the closeness to this is not a sense you want to get. You're just talking about upper limit. And so if you look at the recent DESI result, which I showed you in terms of the dark energy equation of state earlier, and you use those behavior to put a limit, you are basically getting something like 0.07 electron volt. Okay, so you're like, oh wow, we are about to rule out inverted hierarchy. But remember, this is just 2 sigma constraints. At 3 sigma, you'll not rule out inverted hierarchy. At 3 sigma, it will be large enough that inverted hierarchy is still allowed. Plus, there are other complications. So other complications are, so this is just showing the same thing, but in Hubble and sum of neutrino mass space. These are the constraints which I'm talking about from DESI, 0.072 electron volt at 2 sigma. So what happens here, anytime you're doing a Bayesian analysis and you're trying to constrain something which is 0, and if you don't have signal to noise to say definitely that is different from 0, it's a complicated scenario. Now, why it is complicated scenario? If you don't know already what's the, especially if you don't know what is the lower limit of this quantity is. So you have sum of neutrino mass, and let's say this is 0. You could estimate, you could put an upper limit by sampling this, and you'll get some probability distribution, something like that. And you can calculate 2 sigma limit and give a value. So for example, right now we are saying 2 sigma is 0.72. If you don't have any lower limit at all, you could have done, the volume here is not very well estimated. It will depend on how you parameterize it. For example, I can parameterize in place of sum of neutrino, I can do log of neutrino mass, sum of neutrino mass. And in this case, you can now go to pretty much minus infinity, right? In terms of log of 0 is, you have to go to minus infinity. The volume here is going to appear very differently if you work in this space versus that space, and hence your significance is going to look different. And because you have this artificial boundary, and so that's why if you don't have a lower limit, it's a little bit of a hard statement to make. So then you can say, okay, what about if I actually apply a lower limit, which I know in the normal hierarchy case, the sum of neutrino mass is above 0.06 electron volt or 0.059 electron volt, I can draw a line. So now I have a lower limit and I get rid of this problem of different volume. And so when you apply this lower limit, as you can see, because of that kind of issue, the upper limit changes to 0.11 electron volt. And so now inverted hierarchy no more rule out. This is all happening because we have low signal to noise. So anytime you're measuring something which is low signal to noise measurement, you'll have to worry about this kind of thing. So with this kind of prior is what we call it, inverted hierarchy is very close to be ruled out, but not yet. So it's not yet ruled out. And on top of that, if you say, okay, maybe it's inverted hierarchy is true, if you apply that upper limit, then your upper limit of sum of neutrino mass goes to 0.14. So anytime you're talking about interpretation and probabilities of this kind, you have to be careful about what are the choices you are making in prior, especially if you don't know where the boundary is and if you don't have a well-defined Gaussian curve or well-defined curve which has a limit on both sides. If you have only one-sided limit, you have to be careful and pay attention to these kind of details. It's also model dependent. So what we have assumed here is lambda CDM, and there is no other degree of freedom. So equation of state for dark energy is -1. But we don't know what the situation is, right, in terms of the true universe. So if you allow that freedom to also be there, I will say, okay, my dark energy equation of state is not necessarily well known. I'll allow it to be free. Now, when you allow it to be free, there's a lot of degeneracies come in, especially because omega matter is something can be very different in a non-lambda CDM model. And so your sum of neutrino mass goes to even higher limit. So your sum of neutrino mass is upper limit of 0.195, right? So it's even further away. And so given all these issues, what we would like is we would like to be able to measure neutrino mass with more precision, to be able to detect it. And so if you want to detect it, since this is 0.06 electron volt, let's say if I want to detect it at 3 sigma in terms of a lower limit, different from 0, then you want error to be at least 0.02 electron volt. Okay. Unfortunately, if you do a forecast for something like DESI 5-year survey, this is our expected error with BAO and growth combined. So we are hoping that this will get to 0.02 electron volt, at which point you'll be start talking about some lower limit of sum of neutrino mass. If it turns out to be inverted hierarchy, then you'll have a significant detection. But if it's normal hierarchy, you'll not. And so, as always, I can talk confidently about the error, but I can't talk confidently about whether there will be a detection or not. It will depend on how the true universe is. So this is the error bar. This is the error we are going to measure. And so also another interesting thing is that the difference is 0.04 electron volt. So with 0.02 electron volt, you'll not have, you'll not be able to really, if the true value is something in between, you'll not be able to distinguish between them at high significance. You can only distinguish between them at 2 sigma at best. And so that's a problem. So you need to get better if you really want to distinguish them. No, so this exercise we are doing just in the spirit of talking about, okay, what are the different variations and what happens if you do different variation. Right now, you have no reason to actually assume that it's inverted hierarchy. So you not do analysis which completely assuming that. Sorry? How we are varying fraction of energy density? Yeah, so fraction of what you vary is essentially what is the sum of neutrino mass. The sum of neutrino mass will give you what is the fraction of energy density. So it's directly related. So that's one of the equation I showed you. Yeah. Yeah. Not the flavor, no. So flavor are not same as mass eigenstates, so you cannot talk about mass of the flavor. Because they are not eigenstate, they are linear combination. So you can talk about the expected value of the linear combination, but that's not what we are talking about. We're talking about some of the mass eigenstates. Okay, so that's basically all about neutrinos. I would like to now switch gear unless there are questions about neutrinos and talk about a little bit about tidal fields. So this will take you a little bit more details about some of the questions being asked about assembly bias and environmental dependent selections and things like that. So how do we sort of probe this a little bit and try to make justification that whatever cosmology you are measuring is biased or unbiased, or what kind of bias we are going to look. So let's go back to the drawing board and what the story I have told you several times now, but it's always good to repeat. If you think, imagine universe as a distribution of dark matter. So this is an n-body simulation with distribution of dark matter. The dark matter density field is going to collapse gravitationally in different regions, and then we'll get something called dark matter halo. So some of these blue objects are like really massive dark matter halos. And these dark matter halos are the locations where galaxies are forming. So luminous galaxies which you are observing, and we are doing a galaxy survey. So we are seeing these kind of objects. So now if you think about different scales involved in this problem, if you look at very large scale like 100 megaparsec scale, these scales are typically in linear regime, which means the overdensity at 100 megaparsec is very small compared to 1. And so you can just linear perturbatively solve it and you'll get an accurate result. So all your linear power spectrum at large scale, which means small k, is accurate enough, any higher order correction doesn't change that, right? Any higher order correction is pretty much 0, and this is the scale where we also measure BU. Now, when you go to the smaller scales, like something like 20, roughly 20 megaparsec at redshift 0, these are the scales at which the effect of halo formation happens. So there are lots of the overdensity at these scales are now comparable to 1. And so now you need to look at beyond linear correction, beyond linear growth. And what also happens is that one of the complications, once you go to close to the halo scales, then there are lots of multi-streaming. So there are fields which have sort of velocities which are going into different direction. It's not smooth enough, and so you need to evaluate all of that and the effect of that, which becomes hard. And if you go even further, because we are looking at galaxies, so the galaxies are of the order of 0.1 megaparsec at the scale. So 0.1 megaparsec is roughly the scale where we feel we should see the effect of baryons, what baryons are doing, the redistribution, supernova, AGN feedback, all of that should change the distribution of matter at that kind of scales. And so these scales are important to keep in mind, because whenever you're thinking about any sort of physical constraint, you are going to do as a function of scale, and your model will be different complications depending on what scales you are probing. So let's think about, okay, now we are trying to do galaxy survey, and my first statement was that galaxies are tracing dark matter. It's just that it's tracing the peaks of the dark matter. And so all it matters is what is the total dark matter content in the nearby region, or so to say, what is the dark matter halo mass in which galaxies are living. As long as you know that, you can model all of this very well, and the linear bias is a very good assumption. But let's say I want to test this. Maybe my galaxy formation physics is complicated enough that depending on whether you're in an empty region, which is a void, the amount of material available to form and grow galaxies, whereas if you are in a cluster, the kind of high energy environment you're living in, you might see different kind of galaxies, and it's not a linear function. So if I want to sort of try to do that, one of the thing I could do is I could divide this region of space in different kind of qualitatively different quantity. Particularly, what we are interested in is we are interested in figuring out tidal field and impact of tidal field on the galaxies you are seeing and the properties of this galaxy. So you can try to estimate tidal field. The way we do it is that, and again, this will be function of scale. You have to choose some scale. The scale, choice of a scale will depend on how dense your sample is and what kind of galaxies you are looking at. You cannot go to arbitrarily small scale, and you don't want to look at arbitrarily large scale. Arbitrarily large scale, you don't expect to find any of these things. Sorry. Tidal fields, yeah. So if you think about any region in space, let's say around, particularly around dark matter halo, and if there is a test particle, then this test particle is going to experience the gravitational field of this dark matter halo, and most likely to fall inside that. But what is going to happen in terms of, let's say, rather than one test particle, there is two test particles. If there are two test particles, then what is going to happen in terms of the relative motion of these two test particles? So that is going to be sensitive to tidal field, essentially the second derivative of the potential. So what we are trying to ask is that the acceleration of these two particles, whether, for example, in different region, they can be in the same direction and they'll just go together. They can be even region where it's in opposite direction. So the field is diverging, and they will just go to a completely different space. And this can happen in each of these individual axes. So you are talking about three-dimensional space. The tidal field is basically quantifying what is the behavior of two nearby test particles as a function of time. Right? So that's the intuitive feeling. Formally, we can write down essentially the second derivative. I'll show you the equation, which leads you to something like tidal field. And so we want to estimate tidal field. So we start by essentially making a grid in your survey or simulation, whatever you're looking at. We can define this quantity over density, which now we have done probably 10 times. which is the density of galaxies divided by the mean density minus 1. We want to look at how does the density, essentially what is the density fluctuation rather than the total density. So that's what we care about more. You can do, so you do this for doing the measuring power spectrum as well. You can do FFT and calculate this density field in Fourier space. We do Fourier transform just simply because it will be easier to write down the tidal field. You can also write down in configuration space if you want to. And then you can calculate what is called tidal tensor. So this is formally more what the tidal field would look like. The tidal field at any location is essentially second derivative of the potential. And in Fourier space, given it's just exponential to the power minus IKR, the Ks are just going to come out. And so that's the beauty of this. If you have solved Poisson equation in any sort of physical system in your either classical mechanics or electrodynamics course, you must have done this kind of exercise where Ks just falls off. And so this is a tensor. It's in three-dimensional space. This is a 3x3 tensor. You can do the eigenvalue decomposition and find what are the lambdas. And basically, these eigenvalues are the three directions in which the behavior of the two test particles will be sort of orthogonal. And the sign of eigenvalue will tell you whether they are going to converge or diverge as a function of time. Right? So that's the sense we have. Now, using this, you can define a quantity called essentially shear, which is what is the relative values, relative acceleration in these different axes. So some square of that, this is called tidal shear. And you can also define a quantity called tidal anisotropy, which is the tidal shear multiplied by this 1 plus over density to the power minus n, where n is equals to 0.55. So I'll tell you why we are defining this. So what you want to figure out is you want to determine a quantity which is sort of independent from the over density itself. And so that is the reason why we define this particular quantity, and I'll show you how it is independent. So let's say if we go ahead and do this exercise on a simulation. Okay, so this is not a real data. You could actually do this on real data as well, but this is a simulation. And what I've done is I've done this whole exercise, and I've calculated at each point tidal over density as well as tidal shear. For each galaxy, now I have a measurement of over density and tidal shear, and I'm just plotting contours in that space. And what you see is that they are strongly correlated, and this is something expected in linear theory. In fact, tidal shear is directly related to the over density, and so they are very strongly correlated. So if I want to sort of study behavior of, let's say, either properties of galaxy or properties of galaxy clustering as a function of these two quantity, it will be hard because of this correlation. So I'll always have to keep in mind that I'm not varying one of them, I'm varying both of them, even if I'm changing one because of this strong correlation. So it's always nice to go to a space where you can get rid of this correlation, and then you can have a simpler interpretation, easier to look at things. So if you define this quantity tidal shear, and this is precisely why we define it, if you can define this quantity tidal shear, you are going to basically get rid of this correlation. This is over density and tidal shear, and now they are more circular, and I can try to look at properties of a galaxy in this space, and I can talk about each axis more independently. They're still not entirely uncorrelated, but more independently compared to that space. Okay, so this is why we define these two quantity. Now that we have this, let's look at something which I think some of you have asked about, the bias in the selection. So for a spectroscopic survey, you have to first select galaxies based on certain quantity, whether this selection can give you bias sampling of the cosmic wave, right? So what we are trying to say now, if you think about over density, something like delta 8, where 8 is just the scale at which we are evaluating over density, you could do it at a different scale. If you think about high value and low value, so this low value will be regions where there's not much things, right? So if you go to negative over density, then these are the regions where you basically have void kind of structure, so empty regions of the universe. If you go to high values, then these are the regions which are cluster-like regions. So they are very high over density. They are dominating their environment. There is a very big, massive halos in that region, is what you're going to look at. Now, if you think about tidal anisotropy, so defined at, let's say, 5 megaparsec scale. When you are in the low value versus high value for tidal anisotropy, in high value for tidal anisotropy, you are in a region where things are very anisotropic. So you are basically trying to look at whereas in the low value of tidal anisotropy, you are in a region which is anisotropic. So what isotropy and anisotropy will mean? It will basically mean that the gravitational structure there, whether it's very asymmetric or not. And so things like both cluster or void, both are these things are sort of spherically symmetric structures, and so they will give you low value of tidal anisotropy. So they will be here. And things like filaments, like line kind of a thing, or sheets will give you more anisotropic region. So the tidal field is not same in all different direction, and so these are going to be high tidal value. So things like filament and sheets. But of course, these are rough ideas, and there's going to be continuum of these things. So this is how you should think about when you're looking at different parts of this space. And now we need to we want to ask, let's say, if I were to select the galaxies, the kind of galaxies I'm selecting, what is the distribution of these galaxies in this space, and whether this is unbiased or not, right? So I want to first see the distribution. I want to ask, okay, are we sampling all different parts of the universe in an unbiased way, or we are not sampling in unbiased way? We are sampling in biased way, and if you're sampling in biased way, then what is the impact? So this is actually measurement from a real data to illustrate this point. We are looking at different value of overdensity and different value of tidal anisotropy. So low anisotropy and low density is void, low anisotropy and high density is cluster. These are filaments like, and these are sort of low density filaments is what we expect. And what you're saying is that here as a color bar is you're saying what is a fraction of these galaxies which I call LRG, red galaxies. So these are galaxies with not much star formation going on. The reason I'm talking about these particular galaxies is because we are going to do cosmologies with this kind of galaxy. So a lot of DESI galaxies are like this. And the other is what is called star forming galaxy. So even a bigger sample is like this, star forming galaxies. And so we're looking at what is the fraction of these two things. And so the why we are interested in it, if you are interested in galaxy formation, you want to ask, okay, what are the kind of things affects galaxy formation? So typically the old idea initially was that, you know, anything which affects galaxy formation should be sort of local around the scales of the galaxy. But can the larger scale effects, larger scale environment affect galaxy? For example, if something is in a tidally isotropic environment, we'll say anisotropic environment, can that have a different behavior to how the galaxies grow and look, whether they're going to form a lot of star or not? And so you could sort of try to ask this, and by taking the ratio, you're essentially talking about, okay, what is the fraction in this different environment? So what is the efficiency? You can form stars or not form stars as a function of this environment. So that's what this plot is showing. And what you're generally seeing is that in cluster environment, which is actually very energetic and very large potential, generally star formation is hard. You stop star formation very quickly, because to form stars, what you need to do is you need to have cold gas available. So if there is a galaxy and if you want to form stars, there needs to be some cold gas. This cold gas is the reason you need cold gas, because cold gas can collapse and form stars. If you have a lot of energy in this gas, let's say if this gas is hot, then something which is hot will have lots of motion, and so it's something equivalent to what neutrinos do to at very large scale structure formation. The temperature is going to do to galaxy formation. So if something is very hot, you cannot form stars very easily because they cannot collapse so easily. So in most of the feature you're seeing is what we expect from galaxy formation model already. So expect this to be very red in cluster region and blue in void region. But this is the region which is not that well explored. If you have different high tidal anisotropy, then what kind of behavior you're going to look like, and that kind of simplistic argument is not going to be enough. You really need to do n-body calculations to explain something like this. Now let's say, how would I know? Yes. Yes, so we have a spectra for each of them, so we can differentiate from the spectroscopic observation. Yeah, so then we are, so in each of these regions they are actually both. It's all we are talking about, what is the fraction which is star forming versus non-star forming. So this is essentially the fraction of that. In yeah, you don't expect that they live in a particular environment, they live in a continuum, but the fraction of them, depending on what is the general environment, efficiency will be different. So that's what we're talking about. In cluster, there you can find both kind of galaxies, but then can you find a star forming galaxy at the center of a cluster? The general understanding is no, because it's very hard to form stars in that kind of environment at the center where potential is very large, all the material is hot, and whatever was there is already formed a star very quickly. So I'll also touch upon that a little bit later. How can we distinguish this with clustering? But right, and generally the understanding is that in void kind of region you should have, if there is a material, you should have lots of star formation. It should be easier to form stars. Yes. The effect of tidal field on star formation. Yeah, so it depends on at what scales. So at scales of galaxies itself, there are detailed simulation which tells us what it is. But we are talking about 5 or 8 megaparsec scale. This is, if you think about galaxy being a kiloparsec, then 5 megaparsec is 5,000 times larger scale. So 5,000 times larger scale tidal field, whether it affects or not, that's not very clear. So halos are known to be triaxial. The triaxiality is small. For observations, you cannot use this kind of measurement to talk about triaxiality of halos. You have to use different kind of information. There are two reasons to that. One of the reason is because your number density is actually not that large. So if you want to talk about triaxiality of the halo, you need to create that grid I talked about, which is smaller than the size of the halo, to talk about anisotropy within the halo itself. And so if you make such a small grid, you'll get into the short noise. There will be lots of pixels with zero counts. But let's say even if you have high density, which we have at low redshift, there's going to be another problem. What will be the other problem? If you have this dark matter halo and you have measured positions of the galaxy, let's say these galaxies were, these are the true locations of these galaxies, is your measured position going to be something like that or not? Can anyone guess? This is something we talked about yesterday. Redshift space distortion, peculiar velocity, velocity dispersion. So because this is, you're talking about within the dark matter halo, this will have velocity dispersion. They will actually look like finger of God. And if you're looking from here, it will look like an elongated, galaxy. So these, all the distance is going to be missed. So you do not know where these things are. And so you cannot probe these kind of scales in a presence of redshift space distortion, even if you have very large sample. So that is also one of the reasons why we are making grid size of 5 or 8 megaparsec, because at that kind of scales, that effect is going to be not very prominent. But if you are going to sub-megaparsec scale, you are going to, especially if within the halo, you are going to see the effect of redshift space distortion. So your density estimates are not right anymore. And so whatever tidal field you are going to estimate is not going to correct, unless you can have real space position. Okay, so but how would you know that whether this is a fair sampling of the all different environment of the universe or not? What can I do to test this? So what I can do is basically I have to build a model. So I can start with, and since we are in nonlinear regime, typically you have to work with simulations rather than analytical model. I can start with a simulation, and I can first talk about, okay, there are dark matter halos in the simulation, which I know about. And I need to ask, okay, in my survey, what kind of galaxies I'm observing. I need to identify that, such that your whatever quantity you can compare with should be similar. So for example, 2-point function of the galaxies in your simulation and the survey is going to be similar. So there are models to do that. And then you will have galaxies in your simulation. Now these galaxies have same 2-point function as your survey, and as well as same density distribution. So the over density distribution is the same. Now when you say, okay, there are galaxies in this, now you can say that, okay, my galaxies are sampling fairly the cosmic wave or not fairly. So if it's sampling fairly, all you're saying is the galaxies only care about whatever model you have, it's only going to care about the halo mass and nothing else. It doesn't care about the tidal environment, it doesn't care about anything larger scale environment or any other information about the halo. And I can build a model like that, do exactly the same analysis and compare it with this plot. Okay. If I were to do that, build a model like that and compare it, I get something like this, which explains more or less broad features, if you see, cluster versus void, but it predicts a lot more star-forming galaxy in low-density filament compared to there in the observations. And so this means that since my model only care about halo mass, if you were to care about halo mass, you would expect to see different results here. So in the real data, there is an effect which you can now see, which is beyond halo mass, and the real the kind of galaxies we are looking at do care about tidal environment. Okay. So if they do care about tidal environment, now there are two interesting things. If you're interested in galaxy formation, you can go and try to understand, okay, what kind of effects is care about, model that, and then make a statement about how do the galaxy forms and evolve. But if you're interested in cosmology, then you're going to be a little bit scared and say, okay, what is going to be the effect of something like this if I were to infer cosmology with galaxy sample like that, where I have model where I'm doing linear bias and I don't care about the tidal environment in my model. I'm saying that galaxy traces dark matter. Okay, so this is an example where we can see that, okay, tidal environment is something is affecting galaxies, and we want to sort of now think about, there are several such examples, now we want to think about whether this will affect cosmology or not, or you can also go and think about whether this will, it can tell you something about galaxy formation or not. So there are actually another very detailed thing, and that's why I call this advanced topic, which something you can see and talk about, especially when you're looking at this kind of galaxy. So imagine you're looking at galaxies in the universe which are of two kinds, red or blue. So they are either star forming or non-star forming. So red galaxy and blue galaxy. Apart from the tidal environment, can this galaxy care about, or sort of the property of red and blue galaxy will depend on what is the property of this halo itself. Okay. So for example, if you say there are two red galaxy and two blue galaxy in this halo, when it only cares about halo mass, so you have a model where the only parameter is halo mass. But maybe in reality, what might happen is that there is 3 red galaxy and 1 blue galaxy. How do you even sort of think about probing a detail like that, right? So I'm talking about really detail. And so what the statement is that since the center of the halo will again be hot, it will be harder to form stars. You expect that if there are galaxies which are red, then the larger fraction of galaxies will be red compared to, let's say, just a halo mass model kind of a thing. And so you will say that there's a correlation of red galaxy within the one halo. And so you can look at this by looking at, again, a galaxy clustering. So this is the kind of quantity you have already measured, all of you, projected correlation function, which is the integral of 2-point correlation function along the line of sight. And so you can look at the red galaxy autocorrelation, you can look at the red and blue galaxy cross correlation, and you can look at the blue galaxy autocorrelation. And what you'll see is that for the cross correlation, depending on what is the nature of this model, whether it cares about or not, the amplitude of the cross correlation will be function of that. So 2-point function is essentially a powerful tool because you can probe this kind of structure by looking at the cross correlation. So if you cross correlate red and blue galaxy, these are the data points. And if I were to say that, okay, my model do not care about the environment or the environment of the halo it's living in, both red and blue galaxy can form equally likely modulo the halo mass, then that model would look like a red line. And if you were to say that no, it's not, that's not true, I think they care about what is the environment of the halo mass, And depending on what is the correlation coefficient, this amplitude can get suppressed, and so that's the green line. What is it plotting? So it's plotting the projected correlation function. So if you remember, we have calculated the R parallel, R perpendicular, right, from simulation, and we are going to do that with data. And you have also calculated WP. So this is a projection of that. You have also actually calculated this quantity, right? So this is the multipole. This is the projected correlation function. All of this is our integral of the 2D correlation functions which we have calculated. What is plotted here is projected correlation function multiplied by perpendicular distance itself, just to scale things out. Where does red and blue? So what you have calculated is you have calculated autocorrelation so far. So you can take red galaxies and you can calculate autocorrelations of the red galaxy. You can calculate the autocorrelation of the blue galaxy. What this is the cross correlation. So you say when you're doing correlation function, you're taking a pair of galaxy R1 and R2, and you're calculating how many pair you find as a function of distance, and you're averaging over that and normalizing it. Now, when you do this, you say that both of these are coming from the same sample. But now, let's say I have red and blue galaxy, and I'll cross correlate them, which means I'll always consider first galaxy as red galaxy and second galaxy as blue galaxy, and I'll do the same calculation, which is counting the pair of this red versus blue galaxy as a function of distance and construct this quantity. So that's where the cross correlation will come in. So the left and right plot is like autocorrelation function, which we have calculated. The middle plot is the cross correlation function, which you have not calculated, but in principle you can calculate using the same code if you wanted to, if you have two populations. Sorry? No, so this data point, the data points are the correlation function. In the data, you do not know and cannot identify the. No, so you cannot identify the halos of the galaxy. So you're calculating the cross correlation of all the halos. But what's going to happen is that at the scale of the halo, if the two galaxies are in two different halos, they will not be at that distance. That's which is why I'm saying that at small scale you are sensitive to this kind of quantity, and you can see that from the model that there is a difference. Okay, so you can actually, if you wanted to, you can probe these kind of details as well if you're interested in aspect of galaxy formation or impact on cosmology because of galaxy formation, and you have already learned all the tools to do that kind of calculations. So keep in mind, and you can try to think about how that helps with your research. Peculiar velocity, do they depend on the? Yeah, so peculiar velocity should in principle depend on the tidal field. That is right. So depending on what you're looking at, but when we look at redshift space distortion, we are looking at the average peculiar velocity of all different environments. And so when you're doing that, the mean velocity will be average over all different environments, and it's the dispersion which will depend on how anisotropic, if you're looking at different kind of things, then that's what is going to depend on. And the dispersion has a role to play in terms of how your contours looks like in redshift space distortion. Okay, so now going ahead, if we want to sort of go back to look at the impact of something like this on cosmology, I wanted to sort of illustrate this through one particular exercise. If you look at distribution of halos in a simulation, so this is an n-body simulation where there is this is a halo mass, and that's the tidal anisotropy, which we just I described calculated. You know that there is going to be fewer halo at high mass and more halos at low mass. So this is what it's showing. But what is also going to happen is that at high mass, when these halos are massive, like galaxy cluster scale halos, then they are really dominating their environment. So it's not possible for environment to be much different between halo to halo, because they are so dominating and they are essentially isotropizing the thing. The whole region is just dominated by one halo, and the tidal field looks very close to isotropic tidal field, right? So it's which means low value of alpha, and there is not much dispersion. But when you go to the smaller halos, now these smaller halos will be living in other cluster environment, and so they might experience very anisotropic environment. And so this is also going to be the case when you go to look at fainter galaxy. They're living in smaller halos. They might live in very different kind of tidal environment. And so there's a large variety of tidal environment when you go to the smaller mass halo or a fainter galaxy, and all of the current and future survey is going to go fainter and fainter. Right, so the current survey are already, the past survey, all the cosmology result you have seen, established cosmology result pre-DESI, has always been using galaxies which are living in 10 to the 13 or above. But with the DESI era and all other surveys like PFS, 4MOST and everything, and LSST, you are actually starting to, so DESI will probe up to 10 to the 11, galaxies living in 10 to the 11. So you're opening up this just now. And so it's very important to sort of start thinking about what is the impact of this when you go to things like try to study cosmology with that. Which is why analysis is becoming harder and more complicated, because you're opening up this Pandora box here, allowing such variety of tidal field to be sampled. Okay, so now think about if you take a galaxy sample, and this is actually coming from simulation, but it's also connected to a real survey called Gamma survey. And you say that your galaxies are populated, like the probability of having a galaxy is the same kind of thing I showed you in the previous plot, is independent of environment, just halo mass. You'll get a picture like this, where each point represents a central galaxy, and there are stars which represents the multiple galaxy within the same halo. So these are satellite galaxies. All right. Now, let's say I will say that I have a model, and this is just a toy problem for to illustrate it to you. I have a model where I think these galaxies probability of forming in certain region depends on the tidal field as well, which is parameterized by this alpha central and alpha satellite. By setting this to non-zero values, now I will start making populations which are not sampling dark matter density field fairly, which is sampling preferentially certain environment over certain other environment. If I tune this value to very large, then your universe will look very different. So if you go and do a galaxy survey and look at, let's say universe has a model like this, which is strongly coupled to the tidal environment, you'll actually see this kind of structure compared to this, right? So even visually you can see there is a difference. Visually you can see there is a difference because I'm actually showing you a very large effect. That kind of effect is ruled out. You cannot have that kind of, that is strong of a coupling. You can visually see an effect, and hence this will affect all your endpoint functions you're going to look at and cosmology. If you look at the effect which is not ruled out and realistic, which is within the current limit, is something like this, where I have values of this based on what is the best constraint available right now in the literature. And now this does not look like so different from that, but it is mildly different. It's hard to see, right? So now you cannot be so sure because the constraints are that these effects are small, and largely you see is that there is a little bit more emptiness here compared to what is there in the no coupling case. And so let's say if my universe looks like this using this upper limit, and I were to do a cosmological analysis of this sample, I'm going to go and measure redshift space correlation function. I'm going to try to model that with a model which assumes that galaxy traces dark matter, there is no extra coupling, and try to measure things like sigma 8 to mega matter, or f sigma 8, whatever quantity you're going to look at. If I were to go and try to do that, then I will find a result like this, where this is a measurement from weak lensing. This is what Planck CMB shows in the omega matter sigma 8 plane. If my universe do not have this bias, then I'll get this blue contour. if galaxies actually have this bias, this extra coupling, I'll get this contour. And these error bars are actually for a very old survey, 10 years old survey already, gamma. And so what you're seeing is that there is an effect at this error bar, but the effect is small compared to the error bar we had previously. The new error bar which we are going to get with the ongoing survey is going to be a factor of 10 smaller. And so if this kind of effects which you need to test more precisely, and although I'm saying it in a very simple way, just testing this is actually quite convoluted and complicated. If you will test this at 10 times better significance, you are going to see that there is a bias in your cosmology inference. And so you have to be accounting for these kind of things if you're modeling small scale redshift space distortion. This is one of the reasons why redshift space distortion modeling is complicated and compared to BAO. So if I've showed you DESI results for BAO, but I have not showed you DESI results for redshift space distortion because we have not finished that analysis. We are looking at this kind of modeling issues. And so if you are using, let's say if you have a modified gravity model or dark energy equation of state model, and you're using F sigma 8 measurements from these surveys, you have to be careful about these kind of things and check what kind of assumptions they have. They might have multiple measurements depending on what kind of assumptions you have. So even if you're working at the model level, you want to be aware of something like this and use the measurements like F sigma 8 very carefully. Okay, so what I basically so far talked about is there is tidal field is becoming more and more important because we are starting to probe lower and lower halo mass. Just now we are starting to do that, and hence there's a lot of scope to look at things. I've also told you that cosmology can get affected if you are not careful about it. Now I want to show you an example of where you can use something like redshift space power spectrum or correlation function to talk about where are galaxies forming. So the kind of statement I was making about whether the red galaxies can form at the center of dark matter halo which is massive enough or not. Okay, and this is again a modeling exercise, and you can try to there's a lot to do to actually measure these kind of things from data. There's a lot yet to be done. So if you remember, we have already looked at this model. This is the Kaiser model. Power spectrum in redshift space divided by the power spectrum in real space is essentially 1 plus beta mu square, where beta is F over bias. So we have looked at this equation when we are talking about redshift space distortion. And because of the nonlinear scale, there is going to be extra velocity dispersion, which will be modeled by this nonlinear term. Okay, D nonlinear. Given this is the case, now I can go and try to measure this again in a simulation, because we don't want to work with data to begin with. And I can measure this in different kind of galaxies. I can measure this in red galaxies, luminous red galaxy. This is power spectrum, is basically this quantity. Oh, it's labeled here also. This quantity as a function of k perpendicular and k parallel for red galaxies, for blue galaxies, and for a different blue galaxy. So what is the difference? So this is how we are trying to probe a certain aspect of galaxy formation. Now I'm saying that a star-forming galaxy can form, let's say, such that the 2-point function of these two are, if you look at sort of the real space 2-point function of these two, they are going to be consistent, they are going to be the same. It's only the redshift space 2-point function is different. And what we are saying is that in this case, I'm going to impose a condition that these galaxies cannot form in massive halos. So star-forming galaxies cannot form as a satellite in massive halos. That is one of the things we are still trying to sort of understand at what level this happens. There are hydrodynamical simulation which shows these effects, but we do not have a confirmation of at what level this happens in real universe. And this is what is called quenching. Quenching is basically saying that the star formation is getting suppressed in certain environment, particularly in high density environment, in cluster environments and things like that. And so in this model, what I have done is that I've said, okay, I will not form any star forming galaxies in massive halos, but still I will form it in such a way that I will get consistent 2-point function. You have to match that, because your observation will have some 2-point function you're going to match in both scenarios. Then only you can talk about if there's a difference. And if I look at this D nonlinear, which is nothing but if I look at the power spectrum as a function of k parallel, so as a function of k parallel for any k perpendicular, especially at large k, this is very nonlinear scale. This is basically a statement about velocity dispersion within the one halo of a galaxy. So this is what we talked about. I'm taking some large value of k perpendicular and plotting what is this function as a function of k parallel. And so what you see, the profile of this velocity dispersion is a function of, so this is a high mass red galaxy, and so that looks different, that is fine. But mainly I want you to compare these two. So you can see that the behavior, the detailed behavior of these two looks very different. Why is it the case? Because when you're looking at one halo region in redshift space, you're essentially sampling what is the velocity distribution of the satellite galaxy. Now, it will matter whether these are living in a massive halo versus less massive halo, because the velocity dispersion is going to be very different in a massive halo and less massive halo. So when they are not living in less massive halo, it's much more concentrated and much more Lorentzian-like, compared to when they are living in massive halo, it's much more Gaussian-like. And this is a quantity you will have access to from the data. You can measure all of these quantity. Okay. You mean this plot or this plot? So, yeah. So first one is the same thing. Why you are plotting correlation function as a function of r perpendicular and r parallel, right? So in presence of redshift space distortion, line of sight become a special direction. So you want to look at distances along line of sight and perpendicular to the line of sight, and you'll find that these distances are different and there's a distortion. So that's what redshift space distortion is about. Now the same thing will happen in power spectrum space. We could do this in power spectrum space, and here I'm just doing it in power spectrum space, because this kind of mode you'll have access to only in power spectrum space. You'll not be able to do this kind of plot in correlation function space. So we are breaking this in k parallel and k perpendicular just to look at the redshift space distortion. Okay, so this is the kind of measurement you'll have access to. And finally, the last part, which connect to the cosmology, you can take this quantity which you can measure and you can divide it by this DNL. Now what is left is essentially redshift space distortion, which is more or less linear theory, as long as you are limited to a small enough k. And so this should give you Kaiser formula. So even if these are very different galaxies, in our naive model, when galaxies is tracing dark matter, whatever these galaxies are, our statement is independent of that, this should look same, because this is cosmology. They have same cosmology, and even if I'm sampling very different galaxies, these two distribution should look same, and this is where I'm going to measure redshift space distortion or test gravity. If they are same gravity model, this should look same. If I'm changing gravity model, then this two look very different. So all of the effect of galaxy formation I'm trying to extract in this and subtract it out. So as long as you're below k of 0.2, these two should look more or less same. At above k of 0.2, this is not good enough approximation. And so if these two do not look same, then you have an issue. So then you cannot use it to infer cosmology. Oops, I think I exited. Okay, so very good. So that actually allows me to cover more of the detailed thing. Now I'll just sort of show a few of the other ideas which you could use to probe some of these things. So we have been talking about redshift space distortion quite a bit, because it's very interesting to test gravity, as well as it's very useful to do several kind of detailed modeling about galaxy formation and address questions about galaxy formation and quenching and things like that. So it actually helps you in both sides, and so I think that's a great thing to have such a diverse science case. You could also look at now. So I think I've told you in many ways that redshift space distortion is sensitive to a lot of galaxy formation quantity, and hence you have to be careful about. And so if you really want to eventually in future, when you'll have much more precise measurement, claim any deviation from GR, you also need to show robustness, that it's robust against the kind of galaxies you're looking at. And so one of the exercises you could do is you could look at galaxies of different kinds, so red galaxies and blue galaxies, and look at the redshift space distortion signal in different mass regimes, so different kind of mass in the halos. And each time, so these are all data. This is all data, and these are all models. And what you want is that in each of these cases, as long as you're modeling your astrophysics correctly, each time you should get the same F sigma. So you should get consistent F sigma. Then we'll be much more convinced that we are actually able to model our galaxy formation science case a lot. And so this kind of idea should translate to anything you're doing, especially at nonlinear scale. You cannot just do one analysis. You have to think about, okay, how can I do this in many different ways and see if I'm getting consistent result, whether my assumptions are valid or not. Robustness is a key. So in fact, if you write any nonlinear scale related paper, referee is going to ask, how do you know it is robust? You have to show some test that you have done for robustness. And so this is the exercise we did for one of the current survey where we showed how robust redshift distortion modeling is in presence of all different mass scale or different kind of galaxies. So this is galaxy formation, this is different halo formation, different mass scales. And you get our models are describing the data very well for consistent cosmology. So that is the kind of thing you need to do. So now let me change gear and talk about sort of more interesting ideas. Let's go to a regime of black hole. So suppose you have supermassive black holes in the universe, and you want to, and so I'm talking about supermassive black hole, which is relevant for things like PTA and nanograv signal, if you have heard of, but not the solar mass black hole, which are more relevant for gravitational wave. If you have supermassive black hole and you want to detect certain kind of properties. So just to illustrate an idea, if you have a pair of these black holes, when they are going in terms of binary, eventually when they will go into different phases, there is going to be a final kick velocity after they are merged. So you can predict what the kick velocity is if you know certain properties of the mass ratio of the black hole, spin of the black hole. Those are the important quantity. You can predict what the kick velocity is. But in the context of galaxy survey, what can you see in this kind of scenario? So, and these are like very these are not well established, right? So none of the thing I'm saying now is well established. These are just ideas for you to think about. And so what's going to happen because of the kick velocity, this black hole, is it just going to be black hole, or is it going to take any other thing with it, which is visible in visible wavelength, right? So which will emit any electromagnetic light which we can see. And so the general understanding is that the black hole have a region called BLR. This BLR region is emit broad emission lines. So they have generally broad line features, versus it has also lots of things within the galaxy which will emit a narrow emission line around the accretion disks and whatnot. And so if you are able to, if there is a kick velocity which is significant, so that it can move significantly out of it, you're going to see two kind of thing. If the velocity has any component in perpendicular to the line of sight, so it is going to move in the sky, and what you're going to see is that if you can detect this BLR region compared to the rest of the galaxy, you're going to see that this is off-centered from the galaxy. So there are some observations which indicate that these are BLR region which is off-centered from the galaxy, but we do not know. But the other way around is not guaranteed. If you see a BLR region out-centered from galaxy, it's not necessary that's a signature of a kick velocity. Okay, so you have to rule out what are the other possibilities. But in spectroscopy, what you'll also see is that, and if you look at any line, so here, for example, I'm showing you a particular H alpha line here for galaxy. Then this H alpha line will have a narrow component independent of kick velocity and a broad component. But if there is a kick velocity, then, and if this kick velocity have any component along the line of sight, because this is what we are going to sensitive to, this broad component is going to get a redshift compared to the narrow component. So it's going to get shifted. So if you have a very precise measurement in spectroscopy and you can model the narrow and broad component, then you will be able to measure the difference in redshift the difference in redshift will quantify what the kick velocity looks like. So this is an example where these people have done this analysis quite a long ago in 2016, where and this is an illustration, but they have also done in real data, where this is the narrow lines of a H-alpha complex. This is the broad line, and then this is the total line. So in presence of a kick, a relative velocity, as you are going to introduce further and further, this broad line is, I'll finish in a few minutes. Broad line is shifted, the overall nature of this line looks very different, and if it's shifted in the other direction, then again it is going to look different. So by analyzing this overall shape of the thing and model narrow and broad line, you can measure kick velocity of black hole, assuming that that's the cause of it and there's nothing else which is causing. So there are scenarios where the galaxy is very not stabilized and things like that, in which case you'll not be able to do that. So this is a part of SDSS survey where these are all the quasars they have measured, and all these red dots you're seeing, which is of the order of 30 or 40, they show this kind of behavior. So they're saying that these are binary black holes which went through, supermassive black holes which went through merger, and there is signature of kick velocity. Now, it is important just in its own right if you're interested in detecting kick velocity, but it's also important because now this will also help you figure out what is the merger rate of the supermassive black holes in this universe as a function of redshift if you have enough sample, and that will have, then you can predict, okay, how much PTA signal you are going to expect under some assumption, and then compare that to what the amplitude of the nanograph signal is, which is going to become hopefully more precise in future. So you can also do, you can essentially use all the things I talked about, the spectroscopy from galaxy survey and quasar samples in the thing, and do very different science at very different scale. You can talk about black hole, supermassive black hole merger, look at the kick velocity with some caveats. Okay, you can also do very detailed modeling of what we have talked about a lot, which is dark matter halo, but properties of dark matter halo. So let's say you want to talk about what is the slope of density profile or slope of galaxy profile at the core of dark matter halo, or if there is something called halo radius, which is there is some well-defined radius where there are big differences where you can call something is inside the halo or outside the halo. So for this, you can measure what is called splashback radius. This is again, you can measure using the same kind of quantity which you have calculated. You can measure correlation function to much small scale within the halo scale. If you have deep enough sample, you'll have very precise measurements. So this is a measurement from a real data you can see already. And what you're going to see is that in different tidal fields, so these different color, low tidal field versus high tidal field, the slope of the halo profile is different. And you can also look at the derivative of your density. This is the correlation function. You can look at the derivative of this. And if you are going to model that, you're going to find this minima, which is what we call splashback radius. So if a particle is falling into, passing by a halo, it's going to first give a turnaround. And then if it's going to fall inside, then it's going to have a second passage. So the radius at which it gets the second passage is what is called splashback radius, where you expect to find this discontinuity in the density. You'll be able to measure that. So if you're interested in some of the dark matter physics, right now we can't go much further down than this, but very soon we will be able to. You'll be able to sensitive to how the density profile of the halo respond to the tidal field, as well as how this splashback radius scales with the tidal field, which will be function of whatever dark matter physics you are going to put in. It's going to be sensitive to dark matter models. Okay, so with that, this is really the last topic which I really want to show in one slide. So I've talked about a lot of nice things, and this is one of the nasty things when you have to look at surveys like this. So what this is a map of DESI legacy imaging survey. There's a part in the south, there's a part in the north, and this is covered by 3 different imaging area. So if you have a perfect survey and you have created a map like that, what you're going to see, what you should see is that you should see just a small fluctuation, what you're seeing in this area. You should not see this kind of large fluctuation, this tank in the sky and things like that. because universe is not special in different direction. You expect it to be isotropic in all different direction on an average. So you should just see overall fluctuation. But you're seeing all this very large fluctuation. This is what is called inhomogeneity. And I think Paulo talked about FNL. This is actually one of the big challenge to do FNL. So what's going to happen because of this different sky condition and different survey conditions, your depth of the survey varies, and so your efficiency to detect galaxy changes. And when your efficiency to detect galaxy changes at this large scale, you are going to see this inhomogeneity. So this tank is because this is observed through a very different telescope compared to everything else, which has much larger depth. So this is called dark energy survey. There's a tank if you have seen. And so because of the depth, now there's a lot of inhomogeneity. So because of this inhomogeneity, will have a 2-point function. Even if you remove all the 2-point function of the universe, does this inhomogeneity have a 2-point function, which is actually very large scale effect, because you're talking about the full sphere. So whatever you're seeing is a very large scale effect. And if, let's say, you work out and say what is the effect of this on correlation function, if this is the true correlation function, then in presence of this inhomogeneity, forget about this different line, you're going to measure something like that. You can see, ooh. That's a very different behavior. The FNL measurement, which Paulo mentioned for large scale structure, is going to be basically sensitive to these kind of scales, which is can get extremely biased because of these inhomogeneities. And so there are such systematics. So this comes under imaging systematic, but there are several such systematics which you have to be careful about when you're dealing with a survey like this and trying to do cosmological inference. I think with that I will end here, and this is basically summary of all the topics I covered. I hope the summary is useful. I've also sent my slides on Slack, so if anyone is interested in using them, please look at Slack Galaxy Survey channel. As well as I sent a link to tutorials on the Galaxy Survey channel along with all the instructions to install it, and a Fisher matrix script which I promised earlier is also on the Slack channel. So all of that information is available on Slack. Thank you.
So let's thank Shadab for this very comprehensive set of lectures on galaxy surveys. Thank you very much. And of course, Shadab will be here in the afternoon also. There'll be a tutorial, so please continue to bug him. I also want to use this opportunity to thank Sudipta, who has been really doing all the heavy lifting for the organization this program, almost single-handedly. I'm saying this because next week you won't be here. So thank you very much, Sudipta, for all your hard work. No, Shadab, do you want to still more take questions or do it or lunch? What is your preference? If okay, if there are questions, yeah, you feel free to.
All of this will be a function of redshift. We are working at some fixed redshift or some range of redshift. If you have survey which have access to large range of redshift, we can look at different redshift window. And all of these ideas about how the galaxy is forming, what is the impact and what is the depth. In fact, how low you're probing in terms of the galaxy luminosity and the halo mass I told you is also a function of redshift. So, yeah. Mm-hmm. So that's more of a hand-wavy statement so far. We don't know. Nobody has modeled what is the effect of in presence of spin or not. But what has seen is that in some of the simulation, and these simulation do not really resolve the scale of the black hole very well, right? This kind of thing can happen, like the black hole can take a BLR, but there are also other reasons why you can have a disturbance in that. Yeah, so that's also a very good question. So in principle, the tidal field effect should be seen in all scales with some maximum scales. But in terms of actually being seen, it's a difficult thing. We have looked at tidal field effect roughly at 5 megaparsec scale, not smaller than that in this kind of survey. And the reason for that is twofold. One is the density of samples we have. Going to smaller scale become difficult, and then the other is redshift space distortion, because redshift space distortion can move things of the order of even at large scale with distances of few megaparsec. Going below that, now you are going to look at a distorted field. So my Poisson equation, which I used to solve for this and estimate overdensity and tidal anisotropy, is no more valid. You need to have additional velocity term in that. So because of that complication in the data, we don't go below 5 megaparsec when we look at these kind of effects. But in principle, you expect to have the effect at all scales. So amplitude of the power spectrum is a very large scale thing, right? So at large scale, this is sensitive to AS and sigma, in fact. So if you can measure this at very large scale, that simply scales with a redshift. It's a very simple growth, and that is sensitive to AS. Other thing which is sensitive to AS or sigma 8 is growth rate. So as I told you, when you measure redshift space distortion, you measure a combination of sigma 8 and growth rate of sigma 8. So you are sensitive to AS and sigma 8 again. And if you combine, so all of this is degenerate with bias, linear bias. Once you combine it with weak lensing, then you break that degeneracy and you can measure sigma 8.
Okay, I suggest that we break for lunch now and come back at 2 o'clock for the tutorial. Thank you, Shadab.